So in this session, I will try to reproduce all the Minitab graphs analysis we have used in section 2 of chapter 2. Okay, so the first graph we have used in this section 2.2 is we have this histogram and overlaid with the probability density function of gamma distribution, which we try to use to model the behavior of this random variable time intervals between earthquakes. Okay. So we have reading the sample of observations on this variable time intervals between earthquakes. Okay, so we try to produce a histogram. So we click on graph, choose histogram, and here this time we don't just want to produce a histogram. We want to produce a histogram and with the fitted distribution, the PDF of the distribution. So we choose this option, click OK. So we have to specify, we have to tell Minitab in which column we have the sample of observations. So this is column number 1. And here we also have to tell which distribution we try to use to model this random variable. So here, by clicking this data view, you can see here you have to specify the distribution by click on this button distribution. Okay. So the distribution we choose is the gamma distribution. So the gamma distribution. So these are the possible distributions you can fit. So you can choose a gamma distribution. And we already know from the lectures that the gamma distribution depends on 2 parameters, the shape parameter and scale parameter. And if you want to fit a specific gamma distribution with specific values of the shape and the scale parameters, then this is where you should put in these 2 values. If you want the data to decide what is the best value of the shape and the scale parameters, then you leave them blank. Okay, so after that, you just click OK. Now you just click OK, then you should be able to produce the picture. So you can see here we have the histogram, okay, and you have this probability density function of the gamma distribution we can use to model this random variable x. And the data tells us that the shape parameter, the estimate is given by this, the scale parameter beta, the estimate is given by 389.4. Okay, so of course you can edit the graph as you have seen before in the previous Minitab session. You can change, you can define your own bins. Therefore, you get a slightly different histogram, for example. Okay, so that's the first result we have seen in that section. And the second result is we want to produce the probability density function of this gamma distribution, this specific gamma distribution with the shape parameter, scale parameter given by these 2 numbers. And we want to find the probability that for this gamma random variable, this gamma distribution, what's the probability that this gamma random variable takes value between 320.6 and 699.5. Okay, so what we do is this time, again, we want to produce a graph. That's a graph we want to produce. And so that's about the probability distribution plot. Okay, so that graph is about the probability density function of this gamma distribution. So we just click on that. So what we need is to view the probability. So here you have various options, and what we want is we want to calculate the probability. Okay, so we should choose this option and click OK. And so the distribution we try to use is a gamma distribution. It's a gamma distribution. Where is a gamma distribution? So that's a gamma distribution. So we have to specify the shape and the scale parameter. So, well, suppose, well, in that particular graph, we try to reproduce the shape parameter is equal to 1.08. The scale parameter is equal to 450.2. Okay. And so that's a distribution. And we want to find the shaded area. Okay. So this time we want a graph of this format. We want to specify the x. This is what we want, and then we want to specify the x values. X value should be in between. X value should be in between the first value is 320.6. The second value B is 699.5. Okay, so we want a probability in between these two numbers, which is given by this shaded area. So that's what we want to produce. So if we click that, hopefully that's a picture we get. Okay. So here we have the gamma distribution. The gamma distribution with shape parameter, scale parameter, and we want the probability that this gamma random variable taking value in between these two numbers, A and B. Okay, so the probability is given by 0.292. Okay, so that's the second graph in the lecture notes we have viewed. And the next picture, we try to plot the probability density function of several normal distributions. Okay, so let's try to produce that graph. So again, it's a graph, and again, we want the graph is about a probability distribution. So click probability distribution plot. Okay, so we want to produce the probability density function of a distribution of varied parameters for different parameters. So that's the option we want to use. So let's click on that. Then we have to specify which distribution we want to produce the probability density function. So here we want to produce a density function of a normal distribution. And we have to specify the mean. So the mean we have specified in that particular graph, we want to reproduce the mean is equal to 50 or 70. The standard deviation, the sigma, is equal to 5 or 10. Okay, so let's say if we click OK, hopefully we will get the picture we want. Okay, so here we have produced the 4 probability density functions with various values of mean, mu, and standard deviation sigma. Okay, so that's a picture in the lecture notes. So the next result we need to use. Okay, so you can find for any distribution available in Minitab, you can calculate the probability between any two values, A and B, as we have done in this picture. Basically, you can use what we have done here to calculate it for any available distributions in Minitab. You can calculate the probability for that distribution that random variable takes value between any two values A and B. So this distribution, for instance, can be the gamma distribution here, or it can be a normal distribution. And indeed, the normal distribution doesn't have to be a standard normal. Right? So if you want to calculate the probability for a normal distribution, then for example, you can, in one of the example, the variable of interest is the concentration of atmospheric SO2 at a particular location. Okay, so in that example, we want to find the probability of this random variable taking value in between 20 and 30, and we know this random variable has a normal distribution with mean mu equal to 25.8 and sigma 5.5. So we can use the similar method here to calculate that probability directly by using Minitab. Okay, so we calculate the probability distribution plot, and you want to find the probability. Okay. So let's click on that. Then you have to specify the distribution. The distribution is this time is a normal distribution. And we know the normal distribution has mean mu equal to 25.8, and the variance, or the standard deviation, sigma is 5.5. Okay, so that's the distribution. Then the shaded area, you want the probability in between two values, A and B. So A in this case is 20, B is 30. Then you click OK. So that's what you get. You get a probability 0.6317. Okay. And of course, in the lecture we have talked about, we can convert this probability about a general normal random variable x into a probability about a standard normal random variable. You will get the same answer, of course. Okay, so that's a graph we also used in section 2.2. So the next result is we are interested in this variable, the snowfall. Snowfall. Okay, so that's annual snowfall at this particular city, and we have a set of observations. So we try to read in the data set first. So that's a snowfall. So snow. Let's see. That's a data set, I hope. So there's no column name. So unclick that. So we just read in. Okay, so that's a sample of observations on this variable annual snowfall at this particular city. And so what we want to do, what we try to do here. We try to produce a histogram, and by now you should be able to do that. So you can try to produce a histogram, and then you can produce a box plot in the lecture notes as well. And here, what we are interested in is whether we can use the normal distribution to model the behavior of this random variable, annual snowfall at this particular place. So we do a normal probability plot. So we produce a normal probability plot. So that's probability plot, that's the graph, that's the option we should click. And because we have observations on one single variable in one column, so that's what we want. Okay. So the sample is in column number 1, and so the distribution we want to investigate is a normal distribution. Okay, so the normal is default, so that's okay. If you want to investigate whether the distribution model you want to use is another distribution, then you can choose another distribution. Okay. But in this case, it's a normal we want to investigate. So click OK, then click OK. So hopefully that's the normal probability plot you get. And in this case, you can see all these points fall pretty close to this middle straight line. Okay, and these two curves, this lower curve and this up curve, really tells us that if the points all in between these two curves, then that probably tells us the points, all the points fall close to this middle straight line. If some points falls outside of these two curves, then probably we can't say these points fall close to a straight line. Okay, so these two up curve and a low curve gives as some sort of objective means to judge whether the points fall close to the straight line enough or not. Okay, so the conclusion in this case, the points fall close enough to the straight line, therefore the normal distribution is a reasonable, sensible distribution to model the behavior of this random variable, the annual snowfall at this particular location. Okay, so the next picture is the rainfall data set. Okay, so this time we want to investigate another data set which contains observation on rainfall. Okay, so let's read in that data set. So it's rainfall, so rain, hopefully that's a data set. So there's no column name. So we read it in, so that's a rainfall data set. We have a set of observations on this variable. The rainfall, amount of rainfall in March at Minneapolis. City St. of the state of Minneapolis. Okay, so this time we ask whether we can use the normal distribution to model the behavior of this random variable. Okay, so again we can produce a normal probability plot. And the distribution is normal. We try to see normal whether it's suitable model. Okay, so we click on that. Then in this case you can see that because clearly this point fall outside this low curve, okay, and this point is slightly below the low curve. So therefore in this case we can no longer claim that these points fall close enough to this middle straight line. Therefore that indicates the normal distribution probably is not a very sensible distribution to use to model the behavior of this particular random variable, the rainfall, amount of rainfall in March at this particular setting. Okay, so we try to use the log normal distribution. So the log normal distribution, you can get a feeling how the probability density function of the log normal distribution look like by plotting the probability density functions for various parameters of the log normal distribution. Okay, so if you want to do that, you can produce a graph of probability distribution, and you want to plot several probability density functions for different parameters. So you click that option, and the distribution this time is log normal. So log normal, and so you can choose try some different values. Okay, so you can try location. Okay, let's just try, I don't know, try some 4. Okay, so let's set a scale parameter equal to 1 and try different location parameters. Let's see, so that's a sort of, we have 3 different probability density functions for the log normal distribution with different location parameters. The scale parameter is equal to 1. Okay, so you can see you have 3 curves. Okay, so this log normal distribution basically tells us lots of observations here, but because this tail doesn't go to 0 very quickly, it goes to 0 slowly. So that indicates that there are possibility that you have some very large observations here. You have few large observations, okay, because basically this curve doesn't go down to 0 very quickly. It's very tail off slowly. Okay. So that's a feature of the log normal distribution. So for this sample of observations on rainfall, we want to investigate whether the log normal distribution is a suitable model. So we do a probability plot. The distribution is log normal in this case. Okay, and so that's the probability plot against this log normal distribution. Okay, so you can see that this time all the points fall in between these two curves. So we can conclude that all the points fall close enough to the straight line. Therefore, we think the log normal distribution is a sensible model to model the behavior of this random variable, the rainfall in March to this particular city. Okay, so therefore we can go on to use this log normal distribution to take the various probabilities. Okay. So the next example, we're talking about the Weibull distribution. We're trying to learn the Weibull distribution. So it's always a good idea you can plot the probability density function for various parameters of the Weibull distribution, then to get some ideas how this probability density function look like. So in this case, we want to plot some probability density functions of Weibull distribution, okay, for various different values of the parameter. So that's what we use, and we want to get some idea about the Weibull distribution. So the Weibull distribution is here, and so you can try different as we have learned that the shape parameter is more important, which determines the shape, while the scale parameter is less important. The scale parameter is just, you think there's a spring which allow you to expand or shrink on the x-axis, but it doesn't change the shape of the probability density function. So let's try different values of shape parameter. 0.5, 1, 2, 8. Okay, so the scale parameter, let's fix 1, then let's. So you can see we have various 4 different probability density functions corresponding to different values of the shape parameter, while the scale parameter beta is fixed at 1. Okay, so you can see really the Weibull distribution can assume various different shapes. Okay, so this density function in blue is somehow similar to the log normal. Lots of observations, very small, but there's a possibility there are some extreme large values because the density function tail off slowly. Okay. While this density function in purple looks somehow similar to the normal distribution. Okay. Not exactly bell shaped, not symmetric, but it's close. Okay. So from this picture you can see the Weibull distribution, the density function can have various different shapes. Okay, so in this particular example, you want to look at the data sample observations on this variable, the stress from wave action on the joints on an offshore oil rig. We have a set of observations on this particular random variable. So let's read it in this data set first. So stress 1, no column name. Okay, so that's a data set. Okay, so we want to see whether a Weibull distribution is a suitable model for this random variable. So we just do a probability plot. So produce a probability plot. Okay, so we have observations in one column on one variable. So that's the option we have. So all the observation in column number 1, the distribution should be the Weibull distribution this time. Where's the Weibull distribution? Is here. So So that's the probability plot against this y-bar distribution. So because all the points are in between the two curves, so we can say that the points are fall close to this straight line in the middle. Therefore, we can say the y-bar distribution is a reasonable model to model the behavior of this particular random variable, on which we have a sample of observations in this column C1. Okay, so of course, in this case, we also have the estimate of the shape parameter alpha, the estimate of the scale parameter beta. Okay, so if you want to plot the probability density function of this specific y-bar distribution with these two parameter values, then of course you can do that. Okay, and you can also calculate the probability, say, for this specific y-bar probability distribution or random variable, its value less than 60. You can find this probability using what we have done before, similar to what we have done before. Okay, so this time you want the probability in between two values, okay, for a y-bar distribution, rather than in this picture we have the gamma distribution. Okay, so you can do the graph. You want to calculate the probability, and you want the probability to find. Okay, so the distribution is a y-bar distribution with the shape parameter. The shape parameter equal to 0.9832. The scale parameter is 21.85. Okay, so that's the distribution. So we want the shaded area. So the shaded area, we want the probability of this shape. So that's what. And we want the x value is 60. So click on that, let's see what we get. So that's a graph in the lecture notes for this particular y-bar distribution. This is a probability density function, and you can calculate the probability that this y-bar random variable takes value from 0 to 60, okay, which is given by this 0.9328. Okay, so the next distribution we talked about in your lecture notes is exponential distribution. Okay, so the exponential distribution we know is a special y-bar distribution with the shape parameter alpha equal to 1. Then the y-bar distribution becomes the exponential distribution, and of course you can try to plot the density function for the exponential distribution with different values of beta. Okay, so you can do that. You already see we have done similar things before, so you can do that. And the data set we are interested to model is the times between oil spills around an oil terminal in this particular data set called oil spill. So let's try to reading that data set called oil spill. Okay, so that's a data set that we're interested in. There's no column name. So let's reading the data set, oil spill data set. And of course, you can produce a dot plot to see where the observations are on the number line. Of course, you can do that. And if you want to investigate whether an exponential distribution is a reasonable model to use, then you can do a probability plot. So observations in column number 1, the distribution we want to investigate is the exponential distribution. So exponential distribution. Okay. So click on that. So that's probability plot using the exponential distribution. So you can say that, well, although if you use the curve, the bottom curve, the up curve, to judge whether the points fall close enough to the middle straight line, then probably the answer probably is not, if that's the criteria you use. But on the other hand, well, this really, I mean, there are lots of subjectivity involved when you judge whether the points fall close enough to a straight line. Well, so I might say, okay, to me, these points fall close enough to the straight line. So based on that judgment, a subjective judgment of mine, I would say, okay, that exponential distribution is a reasonable model. Okay, so the last distribution we have talked about in this section 2.2 is the largest extreme value distribution. And again, you can plot the density function of the largest extreme value distribution to get some feeling how the probability density function look like. So probability distribution plot. So the distribution we want to investigate is the largest extreme value distribution. And so you can try different location scale parameters. So location can be, say, 0, 5, the scale parameter can be 1 and 2. Okay? So 4 possible combinations. So you would have 4 probability density functions of this largest extreme value distribution, and so how you can see, yeah, these are probability density functions. So for this distribution, you can see that most observations are from here to here, and you tend to have some observations here. So this distribution has longer right tail than the left tail. Left tail is pretty short, so that really means you shouldn't expect too small observations. Okay, all the observations below the mean value, they are pretty close to the mean, but the value on the right of the mean can be some distance away from the mean value. Okay, because of this long tail doesn't go to 0 very quickly. Okay, so this is a similar feature problem. Okay, although this distribution has, compared with this distribution, this purple distribution has large variability. Okay. So the data set we want to investigate is the maximum annual flow of a river at some particular point. So if we read in that data set, that data set is in this data set times okay, so that's a data set we want to read it in, and there's no column name, so we're reading that, and we try to produce, for this data set, we try to investigate whether the largest extreme value distribution is a sensible model to use to model the variable. So we do a probability plot, this time using the largest extreme value distribution. Largest extreme value distribution. Okay, so click OK. Okay. So that's the probability plot you get, and obviously this observation stands out as very unusual because the magnitude of this observation, look at this number line, this is a scale. Okay, so that and this observation is equal to 1,000. Sorry, is 1,065. That's compared with the second largest observation. This is 714. And this the third largest is 600. So this really seems very extraordinarily large. Okay, so of course, extreme values sometimes indicate some interesting phenomena. And of course, you should investigate why this observation is so different, so much larger than the rest of the observations. Okay, so there's a good chance that this observation might be a misrecorded observation. So you can, if you are sure this is a misrecorded observation, you know, then you can try to delete it. Okay, so this observation, where this observation? Wow. Oh, here. So if you are sure this is a misrecording, then you can delete it. Okay? Delete this particular observation, then you do after you delete that, then you do a reanalysis to investigate whether largest extreme value distribution is a sensible model to fit the observation without that unusually large observation. Okay, so okay, and this time that's the probability plot you have after you delete that unusual observation, believing it is a misrecorded observation. Then based on this, you can probably say, well, the largest value, extreme value distribution is a sensible model to use. Okay. And that's more or less all the Minitab outcomes graphs we have used in the lecture notes. Okay, so basically, it's a good idea to always plot the probability density function of a particular distribution to get some idea how that distribution look like. And from the probability density function, you can really look at, understand what's the value you would expect to see when you take a sample from that distribution. Okay, so it's always useful to plot the probability density function to understand better how that distribution behaves. Okay? And of course, for any distributions available within Minitab, you can calculate the probabilities of a random variable taking value in between any two values A and B by using that graph. Okay? And of course, to see whether a particular distribution is a sensible model for based on a sample of observations you have on a random variable, then you can always produce a probability plot using that particular distribution you have in mind. Okay. So these are probably the most important things we have learned in section 2.2. Thank you very much.